This is the 8th video in a series devoted to introductory proofwriting. And we've been going through counting strategies, and we're going to continue to do that for this video as well as the next, focusing on combinatorial proofs in the next. Whereas this one, we're going to look at the inclusion-exclusion principle, as well as something called multisets. So let's start with this inclusion-exclusion principle, which very simply says that if A and B are finite sets, then the cardinality of A union B is equal to the cardinality of A plus the cardinality of B minus the cardinality of the intersection of A and B. And we can visualize this as follows. So if we've got A as this yellow set, B as this red set, then the intersection is in here like shaded in orange. And notice if we were to add the cardinality of A and the cardinality of B, we would double count the cardinality of the intersection. And so in order to only single count the cardinality of the intersection, we need to subtract one copy off. So like I said, it's counted twice, but if we want to only count it once, that's why we have this subtraction of the cardinality of A intersect B there. Okay, so let's start with a fairly simple example, and that is to count the number of elements in the set 1, 2, 3, 4, up to 50 that are divisible by 2 or divisible by 7. So let's put this into the language of some sets first. So let's say that A is all in the set 1 to 50 such that n is divisible by 2. So we could write it in set builder notation like this. But notice being divisible by 2 is the same thing as being even, and we can easily enumerate the elements in this set. So we've got 2, 4, 6, 8, 10, 12, all the way up to the number 50. So the number 50 itself is, of course, even. But how many of these are there? Well, I think it's pretty easy to count up that the cardinality of A in this case is simply 25. You can count that very easily as saying that this is 2 times 1, 2 times 2, all the way up to 2 times 25. So really just we're counting 1 to 25. So now let's look at B. So B is going to be all elements in this set such that n is divisible by 7. So that's our definition there. Again, we can enumerate this pretty easily as well. We have 7, 14, next would be 21, then 28, then 35, then 42, and then 49. In fact, we don't need to do ... here because there's a smaller number. Okay, but let's look at this. This is 1, 2, 3, 4, 5, 6, 7 total elements. So here the cardinality of B is 7. Well, we could count that up pretty easily as well by noticing that this is 7 times 1, 7 times 2, up to 7 times 7. Now let's look at A intersect B, which we can do just by taking the elements of B which are even. Of course, that's going to be 14, 28, and 42. But that means that the cardinality of A intersect B is simply the number 3. Okay, nice. And so now in order to answer this question, we can apply this inclusion-exclusion principle. Notice that answering this question is equivalent to finding the cardinality of A union B. So using this principle, we'll have 25 plus 7 minus 3. So let's see, that'll be the same thing as 25 plus 4, which is 29. So there are 29 such subsets. So there are 29 such elements. Now for another example. And in this example, we're going to count up how many integers are between 0 and 10 million, where they have exactly 4 digits that are equal to 1, or exactly 2 digits that are equal to 9. So let's quickly notice that this being between 0 and 10 million means that n has the following form. So it's equal to a 7-digit number. So let's write this out. So we have 1, 2, 3, 4, 5, 6, 7. And that's where we're allowing 0 to be leading digits. So we would allow something like 0, 0, 0, 0, 1, 2, 3. That would be an allowed 7-digit number in this case. Now, often if we were just to say a 7-digit number, we would not allow a leading 0. But in this setup right here, where we have n between 0 and 10 million, we do allow leading zeros. Okay, let's also notice that 0 is not a possibility in this setup, even with leading zeros, because we must have either exactly 4 digits equal to 1 or exactly 2 digits equal to 9, which means the smallest such possible number would be 99. Okay, so now let's get counting. So let's maybe first look at the condition exactly 4 digits equal to 1, and let's count that up here next to this yellow square, and then we'll look at the exactly 2 digits equal to 9 with a magenta square underneath after we're done with this. Okay, so we've got 7 entries here. We want to choose exactly 4 of them to be equal to 1, so that's using a binomial coefficient. We have 7 choose 4. So like I said, this is choosing the location of the ones. Great. But then after we choose those 4 locations of a 1, we have to fill in the rest of the digits. But how can we fill in the rest of those digits? Well, they can be really anything that we want, except they cannot be ones because it's saying exactly 4 ones. So that means we need to fill in 3 digits from 9 possibilities. Those 9 possibilities being 0, 2, 3, 4, 5, 6, 7, 8, 9. So in total, we have 9 cubed extra possibilities. So this would be the remaining digits. So I'll just put remaining here. Okay, good. So that's the number of ways to have numbers between 0 and 10 million where exactly 4 of the digits are equal to 1. Now let's look at this next case. Exactly 2 digits equal to 9. So I'll do that with this magenta coloring here. Okay, so we need to choose 2 of these 7 placements to be equal to 9. So that would be 7 choose 2. Then after we've chosen 2, there are 5 ones that we need to fill in, and we can fill those in with any numbers except for 9. So that means we can fill them in with the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8. So there are 9 possibilities there. So we have 9 possibilities for each of the 5 remaining. So that would be 9 to the 5 total possibilities left over. Okay, so let's just point out that this is the location of the 9s, and then this right here is the remaining. So it's a little bit tricky because this is locations of 9s and we're using 9 again here, but those are playing different roles. Okay, so this would be like our set A, or the cardinality of our set A. This would be like the cardinality of our set B. And now we need to look at the cardinality of the set A intersect B. So let's put these together right here. So I'll just put yellow square plus magenta square. So that means we need to choose 4 boxes from this set to be ones. So that would be 7 choose 4 because we've got 7 empty boxes to choose. But after choosing 4 of those boxes, there are 3 remaining boxes, but we need to choose 2 of them to be 9s. So from those 3 remaining boxes, we choose 2 of them to be 9s. So let's just point out that here we're choosing the location of the ones, and here we're choosing the location of the 9s, like that. But then after that, we've used up 6 total digits, 4 of them for ones, 2 of them for 9s, which means we have 1 digit left over to fill up. But we can fill that up with any number except for 1 or 9. So that comes from the set 0, 2, 3, 4, 5, 6, 7, 8. So there are 8 total possibilities for that remaining digit. So let's put here, this is the remaining digit. Good. So now we need to use the inclusion-exclusion principle to finish this thing off. So it'll be this number here plus this number here minus that number over there. So let's just write this. So it'll be 7 choose 4 times 9 choose 3, and then plus 7 choose 2 times 9 to the 5th power, and then minus 7 choose 4 times 3 choose 2 times 8 to the 1st power. So I won't calculate that up, but you can use the formula for binomial coefficients to easily calculate that up. It's going to be a fairly large number, so you probably want to use some sort of computational device. Now, what I will say is there seems to be something fishy going on here, because what would happen if at this step right here, we first chose the location of the 9s, and then after that, chose the location of the 1s. Well, choosing the location of the 9s, we would have 7 choose 2. And then choosing the remaining location of the 1s, we would have 5 choose 4, because we've got 4 locations to choose again. And it seems like we would get a different number, but in fact we don't get a different number because this is one of those binomial coefficient identities. So you can check that those two are the same. And in fact, there's a more general identity, which is a nice homework problem, which you might have in whatever course you're taking, and you'll definitely have in the course that I'm teaching. So now that we've done a couple of these inclusion-exclusion examples, let's move on to talk about multisets. Now we're ready to explore the notion of a multiset. So let's look at a definition. A multiset is a collection of objects which may be repeated. So this is kind of a generalization of a set and a list. It lies kind of in between a set and a list. Let's recall that objects in a list can be repeated, but the order matters in the objects of a list. Like 1, 1, 2 is thought of as being different than 1, 2, 1. Whereas in a multiset, that's not the case, as we'll see with an example. Then that repetition can be recorded in a multiset by the notion of a multiplicity. So the multiplicity of an element in a multiset is the number of times it occurs. So let's look at this very simple example, as well as some notation that we can build out of this example. So let's say we've got the multiset, which I'll call capital X. We'll use the notation where we have these square brackets. So that's different than what we used for lists, which was round brackets or parentheses, or for sets, which was curly braces. So here X is the multiset AA, B, 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 C. So there are 6 elements in this multiset. It just happens that 2 of them are equal to A and 3 of them are equal to B. So that means A has multiplicity 2, which we'll denote like this, M sub X, so X is the name of the multiset, of A equals 2. So that's the element right there. Then the multiplicity of B is 3, so that's what we would read here, and the multiplicity of C is 1, because it only occurs once. You might read this holistically as the multiplicity of B in X is 3. Now, I'd also like to point out that we could write the multiset X in a different ordering if we wanted to, and it's still the multiset X. So we could indeed write it as B, A, B, A, B, C. So there are 2 A's, 3 B's, and a C, and that's all that matters. Furthermore, I'd like to point out that any set is a multiset. It's a multiset where everything has multiplicity 1. Okay, so since we're talking about counting, we want to move up towards counting certain multisets. And we'll start that with an example. So let's say we've got a 3-element set and we want to find all multisets that contain elements from this 3-element set. So let's start with 0-element multisets. Well, there's only one 0-element multiset, and that's the same thing as the 0-element set, which is the empty set. Okay, now let's look at 1-element multisets. Well, 1-element multisets are just singletons, just like 1-element sets. If you only have one element, there's no opportunity for repetition. So here we would have 1, the multiset 2, and the multiset 3. Of course, we could write that in curly braces because multisets and sets are the same when they have either 0 or 1 element. Now let's look at 2-element multisets. So we've got more of them here. We've got like 1, 1, 2, 2, 3, 3. So those are all of the ones that are not sets themselves. We have repetition. But we could also have 1, 2, we could have 1, 3, or we could have 2, 3. So those are all the ones that turn into sets. They do not have repetition. Okay, so next up I want to introduce some notation, and this notation will help us eventually count the number of multisets. And so let's just get into writing this notation and then we'll explain how it works. So I'll denote this multiset 1, 1 as star, star, and then bar, bar. So this means that there are 1, 2, 1s, but there is 0, 2, and 0, 3. So I'm separating the elements 1, 2, 3 by these bars right here. And so depending on the placement of the bars, that tells me how many 1s there are, how many 2s there are, and how many 3s there are. So now let's look at 2, 2, the multiset 2, 2. So that would be bar, star, star. That's how we would denote that. And that's because there are 0 1s, so there's 0 stars right here. That denotes the number of 1s. There are 2 2s, and there are 0 3s. Okay, well, let's look at 3, 3. So that would be bar, bar, star, star. So reading into this, since there are 0 stars in this location right here, that means there are 0 1s in the multiset. There are 0 stars in this location right here. There are 0 2s in the multiset, but there are 2 stars here. That means there are 2 3s in the multiset. Okay, let's move on to the next one. So 1, 2. So that would be star, bar, star, bar. So this placement right here is for the number of 1s. There's 1 of them. This placement right here is for the number of 2s. There's 1 of them. This placement right here would be for the number of 3s, but there are 0 of them, so that's left blank. Okay, so let's look at 1, 3. So that would be star, bar, bar, star. Notice the place that would count the number of 2s is empty because there are 0 2s. Okay, finally, let's look at the set 2, 3, the multiset 2, 3. So that would be bar, star, bar, star. So this spot right here that would count the number of 1s is empty. So now let's look at 3-element multisets. So let's start with 1, 1, 1, and 2, 2, 2, and then 3, 3, 3. So those are all of the multisets that only contain one type of element. They all contain 3 elements, but only one type of element. And we could put this into the star and bar notation as follows. So this first one would be star, 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 bar, bar. So the location where we count the number of 1s has 3 stars. The location where we count the number of 2s and the number of 3s is empty. Now let's look at this next one, 2, 2, 2. So that would be bar, star, 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 bar. So where we count the number of 1s is empty, the number of 3s is empty, the number of 2s, there are 3 of them. And then finally for 3, 3, 3, we would have bar, bar, star, star, star. Again, the place where we count the number of 1s is empty, the number of 2s is empty, but the number of 3s has 3 stars. Okay, so let's get a little bit more interesting. Let's maybe look at the multiset 1, 1, 2. So that's definitely a 3-element multiset. So that would be star, star, bar, star, bar. So again, we're counting 2 1s, 1 2, and 0 3s. Okay, so let's do a couple more. We won't totally enumerate these, but we will do enough to get an idea for what's going on. What about 1 3 3? So there's a single 1 and then 0 2s and then 2 3s. So the place where we count the number of ones has a single star, where we count the number of threes has 2 stars, the place where we count the number of twos has 0 stars. So that would be the star bar diagram for 1, 3, 3. Now let's go ahead and look at some 4-element multisets from, like I said, the set containing 1, 2, 3. And I just want to be clear that this is not a full enumeration of the 3-element multisets. It might be a nice warm-up exercise for you to write down the rest of them if you'd like. Okay, so now let's look at some 4-element ones. I'll just say that there are 15 in total, and we'll be able to calculate that later, but just like I did not enumerate all of them here, I won't enumerate all of them here. I think it'd probably be a good exercise for you to as well. Okay, so let's maybe look at this one. So 1, 1, 1, 3. So that's definitely an example. So let's see, we would have 3 stars in the 1 position, then a bar, 0 stars in the 2 position, so that means there's 2 bars next to each other, and then a single star in the 3 position. So that would be the diagram for this multiset. Okay, let's look at another one, maybe 1, 2, 3, 3. So there's a single star in the 1 position, a bar, a single star in the 2 position, a bar, and then 2 stars in the 3 position. That's how we would count that up. So let's maybe look at 2, 2, 3, 3. So that's kind of an interesting multiset. So it only contains elements from 1, 2, 3. It's missing 1, but then it has 2 each of 2 and 3. So that would have 0 stars in the 1 position, and then 2 stars in each of the 2 and the 3 position. So that would be our diagram there. So I said there are 15 in total. We've done 3 of them, so that means there are 12 left. Again, that would be a nice homework exercise. Okay, so now that we've kind of explored these multisets quite a bit, I think we can probably count up how many there are in general. Now we're ready to count k-element multisets from an n-element set. That leads us to the following claim. That is, there are n plus k minus 1, choose k-element multisets from the set containing 1, 2, 3, 4 up to n, or really any n-element set. That being said, if you've got an n-element set, it might as well be equal to 1, 2, 3 up to n, especially if there's no additional structure to it. Now, some of you may like to learn extra notation. I know that when I was a student, I liked to learn extra notation. And in fact, there is notation for this number of k-element multisets. And it goes like this. So n plus k minus 1 choose k is this kind of like, I don't know the name of it, but it's this binomial coefficient where you have an extra parentheses. And furthermore, you can check this, but it's equal to n times n plus 1 all the way up to n plus k minus 1 over k factorial. But this is very, very close to a normal binomial coefficient, but instead of having a lowering factorial or a descending factorial, a falling factorial of k terms starting at n, we have what's called a rising factorial of k terms starting at n. So notice this is the product of k terms, n times n plus 1 times n plus 2 all the way up to n plus k minus 1. Where we start at n. And just as we saw earlier notation for this falling product, which was k underline, there's notation for this rising product of k over line. Okay, so like I said, this is just some bonus notation for those that are interested. I know that I was super psyched about things like that when I was a student. Okay, so let's maybe do a little bit of a proof of this claim. So let's maybe suppose that A is a k-element multiset from the set containing 1, 2 up to n. Now I'm going to introduce some notation for A. So I'll write A as follows. So it's going to be the multiset 1 to the m1, 2 to the m2, all the way up to n to the mn. So those don't really mean exponents. I'll show you what those mean. But these need to satisfy a certain rule, and that is m1 plus m2 plus all the way up to mn is equal to the number k. Okay, great. But what do I really mean by this notation? So let's be careful to sort that out over here. So the multiset, which would be like 1 cubed, 2, 4, and then 3, 2, would be the multiset where we have 3 1s, 4 2s, and 2 3s. So in other words, it would be 1, 1, 1, 2, 2, 2, 2, and then 3, 3. Okay, so that's just some shortened notation for this multiset. I don't know how common it is. I know it's like sort of common to use these exponents for repeated appearances of numbers when you're studying integer partitions. And I know something about integer partitions, so that's where I'm taking this notation. Okay, so now what we will do is take this multiset and attach it to one of these diagrams. And then we can count the number of such diagrams. And after counting the number of such diagrams, well, that'll be the number of such sets, and we'll be good to go. So what would the diagram be? Well, it'll be one of these star and bar diagrams where we have m1 stars in the 1 position, m2 stars in the 2 position, and so on and so forth. So it would look something like this. Star, 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 so a bunch of stars, and then a bar, and then a bunch of stars, and then another bar, and then that ends with a bar and a bunch of stars. So something like this. And like I said, this denotes the first position, so the position of the number of 1s. So that means there are m1 total stars here. Then this is the position for the number of 2s, so there are m2 stars there. And finishing off way down here, this denotes the number of n's, so there are m sub n number of stars here. So there's a really important thing to note here, and that is if we take out all of the bars, there are exactly k stars. So let's point that out. So there are exactly k stars. Great. And then how many bars are there? Well, notice the bars separate the number of 1s from the number of 2s, from the number of 3s, all the way up to the number of n's. So that means we have exactly n minus 1 bars. So let's write that down. N minus 1 bars, because there are n minus 1 places between each of the numbers. There's a spot between 1 and 2, there's a spot between 2 and 3, there's a spot between 3 and 4, there's a spot between n minus 1 and n. So now putting this together, we can see how many characters there are, and that would be the sum of these two objects. So there are exactly n plus k minus 1, like I'll say there are characters. So really we're thinking about making a word, and that word has n plus k minus 1 characters, but there are only 2 possible letters. You could have the letter which is a star and the letter which is a bar. And now we're ready to finish off our counting, and it goes like this. So from the n plus k minus 1 characters, we choose, let's see, k of them to be stars. But how many ways are there to choose k objects from n plus k minus 1 objects? Well, that's exactly the binomial coefficient which we learned about in the last video. So that leads us to our result, which is there are n plus k minus 1 choose k such choices. And each of those choices gives us a new multiset. So that counts the number of multisets. But you might worry a little bit right here, and you might worry because what if instead of choosing the location for the stars, we chose the location for the bars? Notice that we'll choose n minus 1 spots for the bars, which would give us the binomial coefficient n plus k minus 1, choose n minus 1. Well, in fact, those two are the same number. So let's put that in here. This is the same thing as n plus k minus 1, choose n minus 1. And that's from a binomial coefficient identity, which likely you saw on your homework. Okay, so that clears up the proof of this result. Now let's do some examples based around this. So our first example will be to count the number of non-negative integer solutions to the equation x plus y plus z equals 17. This is an example of something called the linear Diophantine equation. So what we'll do is start with the solution, attach it to a multiset, and use that to come up with some sort of counting argument. We know we should attach it to a multiset because, well, of course, we're looking at examples involving multisets right now. Okay, so let's look at a solution, maybe x equals 10, and then y equals 5, z equals 2. That's most definitely a solution because 10 plus 5 plus 2 is equal to 17. Okay, so now, like I said, let's attach this to a multiset. Well, maybe we'll first attach it to one of those diagrams, and after which we'll attach it to a multiset. Well, maybe the diagram could be something like this. Star, 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 star. I'm making 10 stars, by the way. So 1, 2, 3, 4, 5, 6, 9, 10. And then, so this would represent the value of x. And then this line would be kind of like the plus sign. And then we'll have the value of y, which is 5, so star, 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 so 5 stars, and then 2 stars for the value of z. And in particular, what you can think about this is having 17 stars and then choosing where to put these 2 bars. And those 2 bars will split your number into x, y, and z. But let's notice that this corresponds to the following multiset. So instead of using 1, 2, 3 here, I'll use x, y, z. So this would be the multiset x, x. Well, how many of them? We'll have 10 of them. And then y, 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 y. So we have 5 y's. And then finally, we'll have 2 z's. Great. So let's notice that this is a 17-element multiset from a 3-element set. So that tells us how many solutions do we have? Well, we'll have 17 plus 3 minus 1. Choose 17. So just to reiterate what I just said, this is a 17-element multiset from x, y, z, a 3-element set. So of course that's going to be 19, choose 17, and you can work that out and it'll be 171. Now we could also use the notation that we had before over here. This is equal to 317, where we have this different type of binomial coefficient. So this would be a rising product starting at 3 for 17 total terms. And so let's see, that's going to end at 19, and then it'll be over 17 factorial. Again, that's from this like bonus notation over here. Okay, so let's look at a generalization of this example. Okay, so now, like I said, we're going to look at a generalization of that example. Let's look for all non-negative integer solutions to x1 plus x2 plus x3 up to xn equals k. Okay, so this is the same sort of idea. Okay, so let's say that we have a solution, and our solution is xi equals mi. Now we can take that solution and attach it to a multiset. The multiset would look something like this. So it would be x1, x1, and there would be exactly m1 of these. And then it would be x2, a bunch of x2s, and there would be exactly m2 of these, all the way up to xn, xn, and there would be exactly mn of these. But what is that really doing? Well, how many total entries are there in this multiset? Well, since xi equals mi is the solution, there are m1 plus m2 plus up to mn total elements in this multiset, but that's equal to k. Again, that's because this is a solution to that equation. So what are we doing here? Well, we're finding multisets with k elements from n total elements. So let's see, each of these corresponds, like I said, to a k element multiset of an n element set. That n element set is written as x1 up to xn. So we know exactly how many of those there are, and those are n plus k minus 1, choose k such solutions, because that's the same number as the number of multisets. Okay, let's do another example. Okay, so now I've got an example which actually has a nice geometric interpretation. That geometric interpretation is hard to see in higher dimensions, but it's fairly easier to see in a simple two-dimensional case, which we'll look at. So our goal is to find all integers w, x, y, z such that 0 is less than or equal to w, which is less than or equal to x, which is less than or equal to y, which is less than or equal to z, which is less than or equal to 10. So like I said, there's a nice two-dimensional analog to this, which is, has a nice geometrical interpretation, and it goes like this. Let's say we want all x and y integers satisfying 0, less than or equal to x, less than or equal to y, less than or equal to 5. Well, if we were to graph all of those, we would get this nice triangular shape. So notice this kind of hypotenuse of the triangle is all of the cases where x equals y. That's allowed here. So this would be x and y are both 0, 1, 2, 3, 4, 5. And then filling in the rest of it are the cases where x is less than y. So like I said, we get a nice triangle here. And that's in fact going to be some sort of triangular number. If we were to add all of these up, we would have something like this. 1 from this, plus 2, plus 3, plus 4, plus 5, plus 6. So we have 1 plus 2 all the way up to 6. That would be the total number here. But of course, we're doing this in this larger case. So you could maybe think about the three-dimensional version as some sort of tetrahedral number, right? Because everything would be arranged in a tetrahedron. Okay, so let's maybe think about how we might take certain quadruples here. Well, like I said, we're going to look for x, w, x, y, z, but let's organize them in a quadruple, w, x, y, z. And what we'd like to do is assign each quadruple to a multiset. But let's do that via a couple of examples first before we get an idea of how it works. So let's look at 1, 2, 3, 4. That's definitely a quadruple that follows our rules. And let's organize this into a multiset where we have 10 total entries or 10 elements. And what these numbers are telling us is the location of the bars. So we'll have a star and then a bar after the first star, and then we'll have star, bar, star, bar, star, bar. So like I said, this is telling us the location of the bars. There's a bar after the first star, after the second star, after the third star, and after the fourth star. But after that, there are no more bars. So that means I need 6 kind of free stars here. Okay, great. So notice that this is one of those diagrams for a 10 element multiset of a how many element set? Well, I think it's going to be a 5 element set. So 5 element set. Because notice the number of bars is equal to 1 less than the total number of elements. And in fact, we can turn this into our multiset notation as follows. So it would look like 1 to the 1, 2 to the 1, 3 to the 1, 4 to the 1, and then 5 to the 6, because there are 6 copies of 5. Okay, let's look at another one. Let's say in this case we have 0, 3, 5, 10. So that would be a quadruple satisfying this inequality for sure. But let's say that 0, 3, 5, and 10 are the location of the stars. But now 0, 3, 5, and 10 will be the location of the bars. So that would turn us into the following diagram. We have a bar, and then we'll have star, 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 and then a bar. So this would be a bar in the 0th position, in the 3rd position. And now we need one in the 5th position, so that would be right there. And then we'll need one in the 10th position. So that means we need 5 stars and then a remaining bar. Okay, good. So now which multiset does this correspond to? Well, let's see. I think it corresponds to the multiset where we have 3 2s, and then we'll have 2 3s, and then we'll have 1, 2, 3, 4, 5 4s. So that would be our multi-set in this case. Okay, so let's do one more just for practice. Let's say we have 7, 9, 10, 10. Okay, so that means we have bars in the 7th location, the 9th location, and 2 bars in the 10th location. Okay, so let's see what diagram that will correspond to. So we'll have 7 stars to start off with, just to get us to the first bar. So there we have 7 stars, and then we'll have a bar, 2 stars, and then a bar. So now we have one in the 7th position and the 9th position. And then we'll have a star and 2 bars in the 10th position. That's what we have here. And then which multi-set does this correspond to? Well, let's see. It's going to be 7 1s. So 1 to the 7, we'll have 2 2s, so 2 to the 2, and then a single 3. Okay, so that would be our multi-set in that case. Okay, so I think we've practiced this enough, but notice that in all of these cases, what it boiled down to was finding 10 element multisets of a 5 element set. But we know exactly how many that should be based off of our claim over here. And that is 10 plus 5 minus 1, choose 10. So that's how many total multisets there are, but since those multisets are in correspondence to these quadruples, that's how many quadruples there are. So you can do the calculation here and you'll see what you get is 1001. Okay, so we're gonna do one more counting game before we finish off the video. Now we're gonna look at the number of permutations of elements from a multiset. So we're gonna start off with an example, which is just the number of permutations of an element from a set. And we've done this before, so this shouldn't be new. But then when we move on to a real multiset, when I say a real multiset, I mean one that has a multiplicity larger than 1 for one of the elements, things get a little bit more interesting. So let's start with the number of permutations of the multiset MICHAEL. So that's my name. So let's notice that's a 7 element multiset where the multiplicity of each element is 1. So that might as well just be a 7 element set. But we know how many permutations there are of a 7 element set. There are simply 7 factorial. And that's by some counting exercises we did in previous videos. You can think about having 7 slots to fill, and you'll have 7 choices for this first slot, but then you've used up one of the letters. So you only have 6 for the second, 5 for the third, and so on and so forth. So you get 7 factorial. Okay, so what about the number of permutations of the multiset PENN? So of course we have to be a bit more careful here, and that's because n occurs twice. So what we'll do to start this off is to turn this multiset into a set, and when we turn it into a set, we will differentiate between the two ends with some colorings. Okay, so like I said, we're going to turn this multiset into a set, and that set will be PE, and then we'll have magenta N and then yellow N. Okay, great. So now we really have a 4 element, and now we really have a 4 element set because we're differentiating between the magenta N and the yellow N. And now looking at it like this, there should be 4 factorial or 24 permutations. And now what I'd like to do is list all 24 permutations, but do it in a way so that when we maybe erase the colors, we're left with columns that look like the same permutation. Okay, so let's get started. So let's start with maybe just the standard spelling. So that would be PE, and then we'll have yellow N and magenta N. And then we'll have PE, and then magenta N and yellow N. So that would be 2 of the 24 permutations. But if we were to erase the color here, then we would only have a single permutation of the original multiset. Okay, so now let's maybe try to do this systematically. So let's do everything starting with P first. So we have P and then E. Now let's say we have P and then N. So we'll have P yellow N and then E and then magenta N. That would be an example. And then we could have P magenta N and then E and then yellow N. So that would be another such set of permutations with the colored letters that maybe collapse to the same permutation when we uncolor the letters. So now I'm gonna write down all the remaining permutations on the board, and then we can work towards maybe a general way of counting this type of thing. Okay, so there's all the remaining permutations. So notice we have 24 in total, which is expected because 4 factorial is 24. And here at the moment, we're considering yellow N and magenta N to be different. But I've done this careful pairing. And that careful pairing is maybe like what we'll eventually call an equivalence relation, which will set each of these equal to each other when we erase the color. So let's see, over here we have E magenta N, P yellow N. And here we have E yellow N, P magenta N. But if we were to erase the color, that would simply be E N P N. And that's true for all of these. So let's notice in the end, we have 24, which is 4 factorial, over 2, which is the same thing as 2 factorial total possibilities. But we want to think about this not just as that number, which that number is obviously equal to 12, but how that might generalize to a larger such question. And I think maybe the best way to think about it is like this. So this would be permutations of 4 objects divided by the permutations of 2 objects. Okay, so I think maybe this leading exercise gives us an idea for how to write down the number of permutations of a k-element set where we have certain multiplicities. And so we'll write that as a claim over here, and then we'll talk our way through the truth of that claim. Okay, so here's how we can count permutations of a k-element multiset with multiplicities m1, m2 up to mr. Let's notice if those are the multiplicities, then that means the sum m1 up to mr is equal to k. So the number of such permutations is k factorial over m1 factorial, m2 factorial up to mr factorial. But there's actually a name for that, which is called a multinomial coefficient. And that multinomial coefficient is written as k choose m1, m2 up to mr. But this really only makes sense if r is bigger than or equal to 2. Because if r is equal to 1, it might look like a binomial coefficient, but the left-hand side is not a binomial coefficient. So, like I said, this is only really if r is bigger than or equal to 2 that we would use this notation of the multinomial coefficient. Okay, so here's the idea behind the proof here. So let's say we've got a k-element multiset. And that k-element multiset looks like this. x1, so a bunch of x1s. How many x1s do we have? Well, based off of this, we will have m1 x1s, and then we'll have a bunch of x2s. So how many x2s will we have? Well, we'll have m2 x2s all the way up to xr. How many of those will we have? Well, we will have mr xr's. We know we need x1s up to xr's just based off the fact that we've got that many multiplicities. So what we'll do is take this multiset and then turn it into a set by doing colorings on each of these like equal elements. So we'll color each of the x1s differently, each of the x2s differently, and so on and so forth. But we'll color them via superscripting. So we'll say like the first color, the second color, and so on and so forth. So that's going to turn into the following set. I'll call it x1, x1, 2, all the way up to x1, m1. So that would be all of the x1s. And then we'll have x2, 1, all the way up to x2, m2, all the way up to XR1 and then XRMR. And then how many elements are in this set? Well, based off this sum, M1 to MR, we know there are K elements in this set. And now we count the total number of permutations. So the total number of permutations will be K factorial, because that's the number of K permutations of a K element set. But then a bunch of those permutations are equivalent to each other. And we can get that equivalence by just permuting each of these different colors. So how many different ways are there to permute all of these different colors of X1? Well, there are M1 different ways. So that means we have to divide by M1 factorial, because all of those will be equal to each other. And so we're like making this big multi-dimensional array, if you will. And then how many different ways are there to order these X2s? Well, there will be M2 factorial ways of ordering those X2s, all the way up to MR factorial number of different ways of ordering those XRs. So there's a sketch, and definitely just a sketch, of the proof of this claim. Okay, so now I'm gonna leave you with some warm-up exercises. So I've got 3 nice warm-up exercises for you. The first is to count how many 4-digit positive integers there are with no repeated digits, or if there are repeated digits, all of the digits are odd. And I don't mean all of the repeated digits are odd, but all of the digits are odd. Next is to count how many 6-digit numbers are even or divisible by 5. And finally, count how many W, X, Y, Z integers satisfy their sum is equal to, that should be 100. And then W is bigger than or equal to 5, X is bigger than or equal to 1, and then Y and Z are bigger than or equal to 0. And that's a good place to stop.